Okay, so the question was, how are low and not particularly low determined? Alpha, let's check it out. So here we go. The traditional level of alpha is 0.05. And when I say traditional, it's nearly exclusive. There are virtually no other alpha levels that are ever used. In fact, the only one that's ever used is 0.01. It used to be the case that we might have used 0.10 here and there, but it's used so seldom that even textbooks have stopped addressing 0.10. So it's essentially either 0.05 or 0.01, never anything else. Actually, let me take that back. The one exception might be an alpha level of 0.025 in rare cases, and there's a particular reason for that, but we're not going to sweat that here. So what does that mean? That would mean that if the probability that we obtained a sample mean, given that the null hypothesis is true, is not just low, but is less than 5%, and we can ascertain that on the distribution of sample means, then we will declare that the null hypothesis is not true. We'll reject the null hypothesis and enjoy statistical significance. Now, if alpha was 0.1, it would have to be less than 1%. So we'll operate under that assumption, and we'll treat both 0.5 and 0.1 alpha levels accordingly, as you'll see. But that's what low means. Now, you could say, now, wait just a minute. But that seems arbitrary. And it begs the question of what's hot? That's really hot outside. Well, New Yorkers would say 90 is hot, and of course we wouldn't say hot till 102 here in the southeastern part of Texas. So there is some arbitrariness to it, but it's widely adopted. And honestly, this 0.5 level is derived of agriculture. Some inference testing was done in the realm of agriculture by some very well-known statisticians. That's a hard word to say. Statisticians in the last, 80 years or 100 years or so, very recently, Robert Fisher. And it's born of that. And it's just widely adopted. It's been considered to be sort of the gold standard and very seldom deviated from. So that's what that means. So instead of that paragraph where we say it's low, we say if the probability that we obtained a sample mean, given that the null hypothesis is less than 5%, then we're going to declare that the null hypothesis is not true. And again, we might substitute 1%. But again, we'll get into the mechanics here very shortly. So let's walk through this nonsense with the red shirt. It's a silly example, but textbooks always have cartoonish examples like this. So here's step one. Here are my hypotheses that I know are two-tailed. And you can see I've got that in the header there. The sort of problem we have addressed thus far is two-tailed. The null says that it doesn't make any difference at all. The alternate says that it's going to change it somehow. Wearing a red shirt could actually reduce tips, might increase it, who knows, but there's going to be some kind of change. Now notice that the alternative hypothesis simply states that there's going to be some kind of change. It doesn't specify which direction. So later, we will have a one-tailed hypothesis test, and we'll get into the nuts and bolts of that, which isn't terribly prohibitive. So we'll describe it later, as they say. So here's step one, writing these out. Now, one thing I want you to appreciate is that in this one sample hypothesis test that use two-tailed or one-tailed, we use liberal subscripts. So I make a note to myself, in a sense. I say, well, what's the mean tipping rate in the universe where tips are rendered under conditions of the wait staff wearing red shirts? And that's sort of shown in shorthand with red shirt. So I have to make a note to myself there. I want to really let it be known that this is the universe about which I'm speculating. I just append a little note to myself. That's what the subscript is. And so here goes another part, step two. And again, it's wordy, but this will improve here shortly. Just let me get through this forest. Eventually, the researcher will use the data from the sample to evaluate the credibility of the null hypothesis. The data will either support the null or tend to refute it. In particular, if there's a big discrepancy between the data and the hypothesis, we'll conclude that the hypothesis is wrong. To formalize that process, we'll use the null to predict the kind of sample mean that ought to be obtained given that the null is true. Specifically, we determine, now this is so critical, let me say this slowly. Specifically, we determine exactly which sample means are consistent with the null hypothesis and which ones are at odds with it. And we're going to divvy it up like a piece of apple pie. It'll be no doubters. They'll either fall in one region or the other. For example, the null hypothesis states that the red shirts have no effect on the population mean of tips, and it's still 15.8%, the same as the population for waitresses wearing normal shirts. If this is true, then the sample mean should have a value around 15.8. Therefore, a sample mean near 15.8 is consistent with the null. On the other hand, if a sample mean is far away from 15.8, then we will say it's not consistent with the null hypothesis, and we might reject it. To determine exactly which values are near and which ones are very different from, we're going to examine all of the possible sample means that could be obtained if the null hypothesis were assumed to be true. And that's going to be in a distribution of sample means, of course. For our example, this is the distribution of sample means for n equals 36 misogynistic tippers. And according to the null hypothesis, this distribution is centered at a mean of 15.8. So the distribution of sample means is then divided into two sections, likely or unlikely, if you will. And we'll get to that mechanically here in the next slide.